probability, which is, as you can see, on geometric probability. So geometric probability is being able to find the probability of an event using a geometric model. Alright, first thing we're going to do is take a look at some basic formulas when we talk about what geometric models mean. This means using length or area or volume to help us figure out the probability of certain things. Using length, for example, so if I create a timeline or if I create an actual length, I have a mile and every fifth of a mile is something, So the probability of a certain point lying in that section, right, we'll take the length of that section and divide it by the length of the total. That's probability, the favorable outcomes divided by the total outcomes. For area, if the probability is what's the probability of point P lying in region A, well, here's region A, it's the tiny little triangle. It's a small section of area B, all right? Area B is the whole thing, and area A is just that tiny little triangle part. What's the volume probability? What's the probability of point P lying in solid A? Okay, well, we can see the cylinder is inside the box. So find the volume of the cylinder and divide it by the volume of the big rectangular prism. Now, for those of you that are a little bit worried, thinking, oh my gosh, you don't know your geometric formulas, that's okay. In your Algebra 2 textbook, in the back section, in the T section, on page T10, there are the formulas for geometry. Also, hint, 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 page T7 has your probability formulas. So you may want to look those over as you are reviewing for your test. Let's take a look at our first example. All right, so using a timeline, so using the length idea to help us find the probability of a certain event. The metro arrives at your subway stop every 6 minutes. The train waits for half a minute to let passengers on and off the train. Then the train continues on its route. You arrive at the subway stop at a random time. What's the probability that there is a train waiting for you at your stop? All right, well, let's imagine that we have the timeline starting at 0 minutes all the way out to 6 minutes. And we want to know if the train's only going to wait for half a minute at each stop, let's break those 6 minutes up into half-minute segments. So somewhere in the middle would be about 3 minutes. Obviously, this is not necessarily the most accurate. So 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes. And then in between, we have the smaller half-minute sections. All right? And the train is waiting for us right here at that 1/2 minute mark. So that's the amount of time spent waiting. So the train is waiting for us at that time. So out of a block of 6 minutes, I have a half-minute window. So the probability that I show up at the waiting time while the train is waiting for me is 1/2 of a minute out of 6 minutes, or we can think of it as 1 segment out of 12 segments. If we have 12 30-second segments, one of these segments is the probability. Now, most often, geometric probability is written using percent form. So 1 divided by 12 would be 0.833. Repeating, so 8.3% is our probability. So anything less than 50% goes towards the unlikely phrase. So this is highly unlikely that you're just going to randomly show up and the train is going to be there waiting for you. Usually, it feels to me as if I show up and the train has just left the station. Probably not statistically true, but it just feels that way. All right, so go ahead and try this example on your own, similar to the one we just did. Now, a change to the video, I'm going to have the answer to all of the exercise questions at the very end. So this is problem number 1. So just go ahead and mark that in your book as problem number 1, and then at the end of the slideshow, check your answers. So pause here to read it and answer it, and then continue on when you're ready. All right, so now we're going to use area to find the probability. What's the probability that a randomly chosen point in the figure lies in the shaded region? Well, first we have to figure out the idea of we have a square and we have a circle inside the square. So the shaded region, if I want to know the probability that some point is in the shaded region, I need to know the area of the shaded region and take that out of the total area, which in this case is the square. Because the circle is inside the square, that's everything. So to figure out the area of the shaded region, I'm going to take the square and I'm going to subtract the area of the circle. So area of the square minus area of the circle. So area of the square, of course, is going to be side squared. Well, if the radius of the circle is 5, that means the other side is 5. That means the side is 10. So the square is going to be 100 centimeters squared. Then the circle, area of the circle, is pi r squared. So that would be pi times 5 squared, which is 25. And we generally rewrite this as 25 pi. And again, because I'm having to use a number that's irrational, I don't want to round too soon, so I keep it in pi form until the very end. Let's go ahead and substitute this information in. So the shaded area is going to be the square, the area of the square, minus the area of the circle. All right, and if pi is about 3.14, 25 times 3 is about 75. So it gives you an idea of what to expect in the numerator, out of the total area. So type this into our calculator, and when we do that, the answer we get is approximately 0.2149, I believe, going forward. Move it over twice to get the decimal, or sorry, to get the percent, and rounding to the nearest 1/10 of a percent, this would be 21.5%. So that's the probability that some random point, I close my eye and hit it, some random point is going to be in the shaded region only. All right. Let's take a look at the next example questions. So try these two problems on your own. Again, the formula for area of a triangle is in your textbook if you don't remember it. Pause as long as necessary to solve the two problems, and when you're ready, hit play to continue. All right, using volume to find probability. So when we are using volume to find probability, we have to consider what are the shapes I'm looking at. So there's some vocabulary you need to be familiar with. For example, what's the probability that a randomly chosen point in the rectangular prism lies in the cylinder? So the round thing in the middle that looks like a can, that's going to be your cylinder. Rectangular prism is the box. Rectangular prism is a box. All right? So use those words to help you identify. All right, so we want to know what's the probability that the point is in the cylinder. So we're going to find the volume of the cylinder over the volume of the rectangular prism, since the cylinder is inside the prism. All right, well, volume of a cylinder, go over here to the right and do this, would be area of the base, so that's pi r squared, because the base is a circle, times the height of the cylinder. That's really messy, because I'm using a really fine point. Let's try and change this length of this pen. Pi, there we go, that's a little easier to read. So, looking at our circle, the radius is 1. You can see that's where it's being pointed at. And the height is 2. So put all that together and the volume is 2 pi. Okay? So now let's look at the rectangular prism. So the volume of a rectangular prism. Also area of the base times the height. Since the base is a square, you can say length times width times height, or side squared times height. So 10 times 3 would give us 300 cubic feet. All right, so I simplified this to say pi divided by 150, because I just canceled out, reduced it by 2. And when I type that into my calculator, I get 0.0209. Again, move our decimal number to the right 2 times. So that gives me 2.1%. You always want to round to the nearest 0.1%. So the key to this is going to be knowing your volume formulas, knowing those geometric formulas. So page T10 in your algebra textbook will help you. Surprisingly enough, the geometry textbook works a little bit differently. You discover the formulas, so there isn't a page in your geometry textbook to help you. The algebra textbook is much more useful. Let's move on to our last question. So pause here to take as much time as necessary to read the problem carefully and then figure out the formula. And then when you're ready, hit play and you will see the answer to all 5 questions. All right, that wraps it up. So, 4 questions. I don't know why I said 5. So all 4 questions. If you have a question on any of these, we will cover them in class tomorrow. Or you can always, of course, email me, especially those of you that have been absent due to illnesses. Get well soon and hurry back.